All right, everyone. Welcome to, I think, our third episode of Robo Papers. So super awesome to have Toru Lin, one of the key authors of the paper Sim to Real Reinforcement Learning for Vision-Based Dexterous Manipulation on Humanoids. So thank you so much, Toru, for coming here and sharing your work. Maybe as a start, you can share a little bit about yourself.
Okay, my name is Toru. I'm currently a PhD student at UC Berkeley, working with Professor Jitendra Malik. And before this, I did my undergrad at MIT, also working with Professors Philip Isola and also Antonio Teroga. And currently, my research has been focused on dexterous manipulation and a little bit of whole body control. I work with hardware systems that are either humanoids or basically bimanual arms with multi-finger hands. Yep.
Awesome. Cool. So yeah, maybe we can just dive in. If you can share screen, you can share, maybe just give an overview of this paper, and then yeah, we can go from there.
Yeah, sounds good. So I will start from talking about this paper. So this is the latest work that we've released, a collaboration between UC Berkeley, NVIDIA, and UD Austin. And the TLDR, as mentioned there, is that we present a successful approach to learning humanoid dexterous manipulation using sim-to-real reinforcement learning, achieving robust generalization and high performance without the need for human demonstration. So just first of all, a brief look through all the results we have. So we use a Fourier GR1 robot humanoid, mostly using the upper body. And so 2 arms with multi-finger hands. And then we do a bunch of tasks showing capabilities like pick and drop, bimanual handover, box lifting, also grasping of many different kind of objects. So including out of distribution generalization. And also, I think what I like the most is all the robustness that our method shows, including robustness against random forces, and also robustness when the policy gets disturbed. You see the figures? Nice. So our setup in the real world, there's real robots with 7 dot arms, 6 dot hands, and on it, we equip it with an egocentric RGBD camera and also a third view RGBD camera. And in simulator, we basically set up something that's almost identical with the same Fourier humanoid robot and also with the same hands. And we try to keep the viewpoint the same for the camera. And I will explain later on the details of perception in the task or the policies.
So why do you need the third view?
Yeah, that's a very good question. So actually, it's for perception. So I think a lot of people would think that egocentric camera might be enough. But in practice, there are several downsides that we found with egocentric camera. So first of all, the field of view is actually very limited. So you can imagine for a task like Handover, where you really have a longer range of work place, you need the camera to see further. In this work, so we thought about multiple approaches. I think the simplest one is, what if you just switch out a camera? And then there are also other approaches, like what if you move the head so that you have active vision? But here, I think switching the camera itself is a little bit boring because it doesn't really generalize that much to other scenarios. What if you want even larger workspace or things like that?
So you mean like switching the camera? Sorry.
Yeah, change.
You mean like getting a fisheye camera or something with a wider field of view, I guess? Yeah.
Exactly. That's like a go hack.
Sure,
so it's how trivial if we do that. It's also harder to simulate, which is actually a worse problem. Because I think if we try to use egocentric camera, we also want to use the depth, and then we need to match the depth in sim and in real, and then there will be other problems that come with it. Yeah.
Makes sense.
So we actually, we set up the third view camera so that we can capture the object state with a wider angle, basically. Yeah, this is a TLDR, and in this work, the object state that we take is a combination of the sparse representation, which is the object key point, or central mass, and the dense representation, which is the depth captured by egocentric camera. So we found that there's this very interesting trade-off between these two different object representations. So I think in a lot of previous work, we see either people using sparse representation like key points or dense representations like RGB pixels or depth. But if you think about it, the sparse representation is very nice, it's very interpretable. It's also easier to get, especially in simulation. It's much easier for sim-to-real transfer. But on the other hand, it contains more limited amount of information. So it's harder to train policies that requires a deeper understanding of things like object geometry, object shape, and that naturally limits the expressiveness of the policies. On the other hand, I think the RGB pixel is a very nice representation. It contains very rich information. And depth is similar. It contains a little bit less information, but also pretty good. But then on the other hand, it has very large central gap. So here we try to take the best of both worlds by combining the segmented depth, which is a relatively clean, dense representation that allows the policy to understand object geometry, while supplying also the object central mass key point, which is captured by the third view camera. I'm sorry if this is going a little bit too much into the perception, but hopefully this answers your question.
Yeah, it's good to go into details. So segmented depth, meaning that you run an object detector or something, or segment anything, or one of these models that breaks up the scene into different components that we can then. And so that information, do you know the object classes then, or is it just like instance labels? Is that the?
Actually, we do not know because I think a lot of objects that we test on are out of distribution object. So we actually have a UI for policy initialization where the user just click on the object of interest, and then there's a segment anything at the backend that runs the perception pipeline, identifies the object, creates a mask, and then performs the policy.
So I don't want to get too sidetracked.
I know we're getting into detail, maybe. Yeah. Maybe if I just can sidetrack one last bit. I'm curious, like how. I didn't quite see in the paper whether like you I know there's a lot of like different ablations tests you've done. I wonder what would happen if your third view camera were actually not exact, like were to move a little bit, like, how robust would that be, you think?
That's actually an interesting question. I didn't really test it. My guess is that the third view camera's calibration is actually pretty important because we use that to capture the object center mass. And then the randomness is captured a little bit because we do domain randomization on that in terms of so basically we add white noise to the observed object central mass. So the XYZ, we add like 2 centimeters range of white noise. So that's, I think, the amount of noise that is able to tolerate. We haven't really tested further than that. And then I also have an automatic calibration pipeline to convert whatever object coordinate you see in the camera view to the simulated or the 3D coordinates in the simulator. I usually keep it fairly accurate. So I think it's basically I try to keep it as accurate as possible so that the policy can be deployed robustly. Actually, I think practically, what I found is that if the calibration is off, which is, I think, the scenario that you mentioned, basically the object perception is off. And then you can see policy running like, there's actually an object here on the slightly left-hand side, but because of the calibration is off, you can see the hand actually trying to reach again and again a different point in that space, because what the policy receives is an input saying that, the object is actually here. Which is different from what it sees or where the object actually is.
So I guess,
but that,
I want to let you move on from all the perception stuff. But I guess just so for the sake of restating everything, I think we've got this. So now I think we understand the problem statement, right? So we've got the egocentric camera on the robot's head, another camera which lets you understand where the objects are. You're testing on. You've got this Fourier DR1, which is a nice humanoid with 2 dexterous hands, training sim to real, and we've got you're taking and you're segmenting the point cloud, and you're dealing with out of distribution previously unseen objects, so you don't know anything else. All right, and so no RGB channel, is that right? So you don't know the color, so we're not using that. Yeah, so just object identities basically, which you can get from things like segment anything. So it's relatively easy to get, I guess, and it's a reasonable thing to have. That makes sense. All right.
Yes. Yep. Thank you for the summary. Very nice. Yeah. And I guess RGB in a sense is implicitly used because to run segment anything, we have an RGB view. But then basically to the policy, there's no RGB.
Yeah, maybe Toru, if you were mentioning earlier on, if you can give some background as to the early motivation when you guys set up like this paper.
Yeah, sounds good. So Now that we have an overview of this work, I will talk a little bit about this history or my history of how I arrived at this work. So let me share another paper first, which is a paper called Learning Visual Tactile Skills with Two Multi-Finger Hands. My journey actually started here. And the TLDR of this work is that it's really about how we hack up this teleoperation pipeline. We repurpose two prosthetic hands and build a system. We try to do teleoperation with it, collect visual tactile data, and then train some pretty dexterous looking policies, as you can see here. Actually here. Yeah. So things ranging from wine pouring to steak serving, and also handing over a slippery banana. I think a lot of people don't usually realize how challenging this task is because the banana is actually a toy banana that's very slippery. And for a gripper to grasp it, it's actually fairly challenging. But here you can see the stability that is offered by hand. And also other things are block stacking. And then, yeah, I will just run over these policies again. So I think that was a pretty nice little project that I did in the space of manipulation with spy menu multi-finger hands. And then I think last year was also particularly interesting because a lot of people started looking into this whole building teleoperation system and then learning from demonstration paradigm. So I did that and I found that it's actually pretty nice. You can just collect data and then you train these very fancy looking policies in a short amount of time. But then as I work longer with these systems, I realized a big challenge or a few limitations with this teleoperation and learning from demonstration paradigm, which is that in theory, I think it's easy to solve the problem. For whatever task you can think of, you just build a system, you just do teleop, and then for tasks you cannot solve, you just keep collecting more data. You just train an expert to do better, you just train a teleoperator, and then you can learn the policy. But that's all in theory. In practice, what I found is that there are actually many challenges. So first of all, there are a lot of tasks that cannot be teleoperated or are very hard to be teleoperated. So things like screwing open the bottle cap or things like that. Another challenge.
Those?
Sorry?
What makes it hard to teleoperate those specifically?
Wow, there are so many things. So I think first of all, teleoperation with hands is kind of like an open problem. So in the past year, I'm sure you also saw a lot of different works in this space. There are people who try to use VR, try to use exoskeleton-based system or mocap glove or other things. But it's always very hard to translate faithfully from a human hand to a hardware hand. I think partly it's because we have limited hardware, and partly it's because there's just this retargeting gap that's very hard to overcome. And then there are all these like latency issue. And then there's also like the training curve you need to train a teleoperator to actually do teleoperation with these different devices. It's like playing a game. You need the training time to actually have experts operate the systems. In practice, I think it's harder than people thought. So yeah, I don't think I saw anything that's too dexterous so far. Even for demonstration that I've seen with dexterity, there are also problems like latency that I mentioned, and also with human teleoperating, you always have some suboptimality because humans will be hesitant, humans are not perfect, the trajectory might be not smooth, might be not consistent, and there are all sorts of issues like that. Yeah, so those are the things that I run into. I did this project. Yeah, I'm not sure if I had the same experience or heard similar stories.
Yeah, I imagine it's a very big UX challenge, like for some of these very dexterous tasks. Even with let's say a VR headset, basically you have a bunch of buttons, but you can't express like the full dexterity and all the degrees of freedom that human hands have. Like you say, it's definitely an open problem. And of course, it's so costly to run real world hardware and then get the humans involved.
Yeah, exactly.
Definitely very costly.
Yeah, exactly. And then another problem that I realized is how hard it is to actually get the amount of data to generalize. So I think last year, Aloha from Tony was really popular. And then he also tried to scale up the system in another work called Aloha Unleashed. It's also a really nice work that I really like. But when I look at some of the tables showing the amount of data they collected for a task and the corresponding success rate, it's also kind of pessimistic to me because I remember there was this shirt folding task, which they label as easy. It's not even the hard version. And they collected like 8,000 plus trajectories of it. And the success rate was like 75%. Yeah, so to me, especially as a PhD student, I don't really have access to industrial hired teleoperators. So to me, I was like, I'm not going to do this forever. I don't want to collect more data. And that also kind of relates to my own experience of doing this work. So when we collected these data, we actually realized that there's this expiration dates of each data set that we collect. So one example is that if we collect the data sets, say 100 trajectories of handing over banana, if we do it in the morning, if we train a policy and deploy on the same day, it usually runs smoothly. But after a few days, it just stopped working. And it's very hard to know why. And it's almost impossible to fix it because sometimes maybe someone touched a camera, maybe, I don't know, someone hanged their jacket when we did the data collection and the jacket was removed in a few days or things like that. There are just all these factors. Yeah.
Yeah. Could it just be in the lighting conditions, maybe a cloudy day versus a slightly sunny day?
That too, actually. Yeah, that was surprisingly or not surprisingly important and also very frustrating. Yeah, I remember there was also this work by Chelsea and Sergey, which they did when they were still like PhD and postdoc. And they had to do all the things like data collection and deployment at night so as to best control the lighting condition.
Yeah. Wow.
Yeah. Yeah, so sorry for a very long backstory. Yeah. Yeah, so basically... Yeah,
that's a very good motivation to go to sim to real. Get rid of the
yes.
humans.
Thank you. Yes, well, I felt exactly the same, and that's why I went into RL sim to real. Yeah, so I did another work, which is called twisting lists up with two hands. This is kind of my first dabbling into the space, into this approach. Basically, just wanted to see how far we can get with the resources we had in academics, with the robot and the engineering capabilities and the amount of GPUs we have, how far we could get. Because I think it used to be a case where when people think about imitation learning versus RLSM to real, a lot of people advise me against working on RLSM to real. And usually they will cite examples like the OpenAI Rubik's Cube, because I think a lot of people know that it's a really amazing work, but there's also tons of engineering that went into that work. And so I remember even since my undergrad time, there are professors saying that, oh, of course it works, but it's really overfitting to that single task, that single scenario, with all this engineering that went into modeling, closing the gap and all that. It's impossible for PhD students to do it. Yeah, so I think that was the sentiment. It's getting better. It has gotten better because I think RL sim to real has been more, even kind of a standard approach today for things like locomotion and whole body control. Not so much for manipulation, but I think more people are looking into this space. When I started working on this, it was still considered very challenging. Yeah, so we basically pick a task that people thought was very challenging, and we ourselves couldn't really teleoperate. We couldn't do imitation learning with. So we chose this task of twisting, and we built a pipeline. That's basically the standard sim to real pipeline where we define the environment, we train a policy in the sim, and then deploy in real. And then after this work...
Does it have RGB data? Is this a visual policy that it's learning? I see the biotac sensors on the end, so tactile at least. Is that right?
Actually, no. Yeah, this is pure robot proprioception, which is also pretty interesting that we got it to work from pure proprioception.
Yeah.
We found that, even with just proprioception, not only is this capable of doing this task, it's also very robust. Again, against the force perturbation. It also has a bunch of emergent recovery behavior, which I found very interesting. And also, I was really surprised. And I think this is one of the works that convinced me that I want to keep doing RL because this is where you see all these very interesting behaviors. Yeah. And
So in
then
this case,
But
the
you're
let
doing,
some
but you are
setting-
segmenting it now. Okay.
Yeah.
That's just
and actually, since that, that's when I started doing the segmenting. But in this work, we didn't really use the vision part, which is like any RGB pixel or depth pixel. We simply used 2 key points to represent the object. But it was fine in this task because we're just dealing with bottle-like objects. Yeah. So that was the backstory of that led to this work. So basically, after the twisting work, I realized that, oh, this is actually doable. But then because each project has a scope, so for last work, I basically just stopped at the point where we were able to get the policy working. We were able to show these capabilities, but there are still a lot of things that I felt could be improved. So I basically worked on that further and basically kept improving every components of this pipeline, which became the method of this latest work that I'm introducing here. So basically, for every bit in a sim-through pipeline, I had a little bit of improvement. Basically, just want to make the whole pipeline more practical, more scalable, more useful generally. Because I think after last work, I still heard a lot of complaints of, how a lot of things are just overfitting to a single task, how you're using a more tested hardware, that you're not really putting much effort into things like real-to-sim modeling or generalizable reward design. So here I basically tried harder and got some, again, pretty good results.
generalizable reward design. You're meaning that basically, so before you have an object that's just in like one place and you have to rotate it and you're rotating the lid, and therefore, so here, because you're doing all of these different object manipulation tasks, you could say like, yes, this is actually a route towards real general autonomy. That's
Yeah,
what you're saying? All right.
exactly. Yeah, thank you for a nice summary again. Yeah, so I think here I also got to something interesting, like philosophically. I realized that if you think about object manipulation, you can basically disentangle all the tasks you can think of as 2 things. So one is the contact between your end effector and the object, and the other is the object state, so how you want the object to move. Yeah, so things like, say, we want to grasp a water bottle and move it somewhere. If you think about these task sequence, you can basically decompose it into contact goals and object goals. So you can start by saying that, I want my fingers to touch the bottles in a certain way. And then that's a contact goal. And once you reach that, you care about the object goal, which is the object being moved to a point in space that you desire. And then later on, if you want to do longer horizon policy, say handover, you define the contact goals again, and then object goals again. And I realized that if you just follow this principle, you can go pretty far with reward design. So that's actually how I design a reward for things like handover in a relative short amount of time, I would say. When a lot of people would tell me that, RL is impossible, it's very hard to design reward. But here I realized that it's not necessarily the case if you find a few general principles.
Toru,
It's
can
really
I
nice.
ask, like, so it... sorry. So, Toru, so this paradigm of using, let's say, contact points and then also this object state, right? Do you think it also translates well if the object is deformable, like clothing and things like that?
Yeah, that's a good question. I think actually for the reward design, I will say it's still relevant. Yeah, I think what you need to care about is more on the policy side, but not the reward design side. Because even when an object is deformable, say a piece of cloth, you can still define contact markers like what I did in this work. You can define, there's the color, which is a few points or a point on this object that I want to be in contact with. And you start with that. And similarly, you can define some point on the object. You can track their states and you can say, I want one corner or the other corner of the cloth to be at XY position in space. And you can have a policy that tracks that. I think the challenging part lies in, after you define that, how your policy, your actual control policy, is going to reach the goal. And because the objects of interest might be soft body, might be deformable, it's harder to do that because the point that you care about, the point where you define the reward design, the point that you define reward on might change a lot over time. Once you touch it, it might move to another place. So that creates more problem for the control policy. Yeah. So I think that's actually the larger challenge, but not really something intrinsic about the reward design.
So do you need to know like what specific points to grab the object to make this work? Or is it like something like for the handover, is it just like anywhere on the object is fine? Or is it something I can like ask an LLM or VLM to fill out for me? I'm just wondering how easy it is to do, I guess. Yes.
Actually, extending to having an LM or VLM generate this contact points is a very nice idea. But for this work, what I did was I procedurally generated this marker. But I think there's a very interesting ablation study in this paper that I did, which is if I generate the marker at different places, for example, on a box, then you can see the policy also learns to grasp onto different places on a box. So I will say the marker position or the contact markers is kind of arbitrary. It really depends on where you want the policy to touch. And for the handover, it's the same thing. It really depends on how you want the robot to hand over, whether you want it to grasp at the midpoint of the object or the side of the object or somewhere else of the object. You can just put the contact marker whatever you want it to be. It's kind of like you're mentally teleoperating the whole sequence, but with less effort. You just specify where you want the contact points to be at. You tell the policy to do so, and then it learns to follow. Very nice questions.
Yeah, Toru, actually, maybe you're about to talk about this already. One of the most interesting that I find in your paper was your auto-tune modeling. So how you basically go real to sim and basically don't have to hard code anything.
Yeah.
Could you talk a bit about that, like how the experience went?
Yeah, so that's a good question. So first, I will talk about the motivation of this. So one feedback I got from my previous work was that maybe the work was only possible because you're using a hardware that a lot of people already built model for. So I was using Allegro Hand specifically, which was tested with Sim2Real. So there are all these parameters in Sim and also in URDF, things like joint stiffness, damping, and basically when you do URDF, when you do robot modeling, you try to model each link or basically each rigid body parts on the robots and also each of the joint linkage of the robots. And so I think in the past, people spend a lot of time tuning things like the upper limit, lower limit, the origin of the links, the mass of the link, and all those parameters. I myself also did that. I found it to be very frustrating. And I just thought, is there a way to perform it in a more automatic, more systematic way? And then there's one thing that I realized, which is that when you do model of the robots, you really just care about how we did this modeling as a PhD student in a very relatively dummy version is that we will tune the parameter, we will try to play a trajectory in the simulation, we will track the response curve, which means, we look at if we send it a target position, how well it tracks the position. And then we do the same in the real environment and we see how well it tracks the position. And then we look at things like, the velocity profile, the position profile, and basically just visually match the two of them. And then we just keep tuning the parameters. After doing this for a while, I realized that it really could be automated because when we work with simulator, we can just generate so many different environments in parallel. And why don't we just do that? So it's kind of a very intuitive approach. It's kind of like parameter searching for a neural network, but you do it on the space of physics parameters and URDF parameters. So I define ranges of available parameters to search for, randomly generates URDFs with different combinations of all these parameters. And because we're doing these tests and simulation, we can just do it all at once. Basically just write a script, tune these parameters. I think the most interesting part here is how we are able to generate also different parameters for URDF. Basically everything is in code, so you can always change code programmatically, which is what I did. So the idea is that, we generate different versions of the robot in the simulator environment. We also generate the response curve of these different robots for different environments. And then we only need to do one rollout in the real environment, which is the ground truth. And after that, it allows us to compare all the simulated environments response curve with the real environment's response curve. And then we can choose the one with the lowest MSE across them. to be the kind of like the ground truth environment for a simulation.
I'm curious for this URDF profile, right? Do you end up just using one and then just use that for all tasks? Or do you find that sometimes maybe your URDF just fit it slightly better for one task? It's as if the model behaves slightly differently.
Yeah, that's actually a good question. I actually had a similar hypothesis because of the randomness and different policies. But in the end, I found that there was this, basically when you have a low enough MSE, so for example, there are 100 URDFs that are generated. And then when you compare the MSEs, they're like the top 3 or the lowest 3, basically the best 3s. And they don't really matter, it doesn't really matter that much whether it's the best one or the second best one, because they're fairly close when you search in a huge parameter space. So usually I just stick with the one with the lowest MSE because it works well enough. And I don't need to search an additional parameter, which is switching these URDFs. But there is a big gap. Yeah. Sorry, but there is a big gap. Yeah, the one with lowest MSE and the highest MSE.
Yeah, I was going to ask if how much the trajectories matter, because like I could imagine like my robot policy lifting up its hands over his head. Maybe I get a different MSE if I'm randomly sampling parameters compared to like working in front of me, just because like because different parameters will matter, or unless you actually like really nail the robot values, I guess. Did you ever notice that, or is that not really a practical concern?
Yeah, not really. I guess one technical detail might be pretty crucial here, which is that when we take the task trajectory, so we have this fixed task trajectory on which we calculate these robot response curve matching. So when we define that trajectory, we try to cover, first of all, we try to cover a lot of the workspace. So we try to reach a huge amount of the space. Also, we try to vary the action itself. So we include both more static action and more dynamic action. So I think that coverage of the state space or the state action space allowed us to get pretty accurate MSE in terms of defining how well these simulated environments reflect the real environment. So I think as all robotics work, the devils are in the detail.
So do you want to tell us more about how well it worked? That's what's coming up next, it looks like.
Yeah. So I guess I've gone through most of the parts, and now I'll just show the videos of how well it works. So yeah, I think I've already shown the videos of the capabilities, pick and drop, in terms of task performance. So these are the tasks or policies that we're able to get. Handover, lifting with spline menu, and also grasping of different objects. And one thing I wanted to note is that the one thing I wasn't too satisfied is the dexterity of these hands. So I think they look really nice and they're relatively pleasant to work with. But unfortunately, I think their degrees of freedom is still pretty limiting. They're basically 6-off hands. So yeah, when I wrote the title, I felt a little bit complicated because I really, in my mind, I really don't think it's that dexterous, but it's also as far as I could push with these hands. Yeah, so if you know any more,
meaning like 1, 2, 3, 4, 5, and then 6. Is that right? That's it.
So yeah, 2 offs in the thumb, and then 1 each on other finger. Yeah. So you can imagine that as. I think the most useful applications that I found for these hands are pretty much all grasping adjacent tasks. It can't really do like holding a fork or do things like that.
Right. So to contrast with, so you were showing the video from your the unscrewing the lids, which is with this much uglier looking older Allegro hand, right? But like that one, you really can move everything. Yeah.
Exactly. So it's like unfortunate trick. I think these hands look really ugly, as you said. I totally agree, but they're much more dexterous. And meanwhile, these handless humanoid looks nice, but the dexterity is really not quite there yet. Hopefully, it'll get better in the next few months or years. Yeah. So these are the behavior.
Sorry. I read in your paper you mentioned something about like basically training using task-aware hand pose as priors. And you mentioned something in the paper that is pretty important. So could you talk us through a little bit about that? Like what exactly is task-aware like hand pose?
Actually, yeah. That's a good point. So basically, I use this term because I really want to differentiate this part of the method from things like initializing from a full demonstration trajectory, or really a data set of curated pre-grasp, which is what I think people had used previously to accelerate the sample efficiency of RL policy learning. So what we found is that instead of doing all that, for which you really need a lot more engineering efforts, what you can do is simply, it's kind of like pre-grasp, but I will say it's a more free-form representation than pre-grasp. You can just have a human connect a teleop in simulation. You have a human play around the object just to collect some task-aware hand post initialization, which means realistic placement of the wrist around the object that a real human will do. So that might sound a little bit stupid, but in practice, we found that that really simple thing could accelerate policy learning by a lot. I think it will just reduce the exploration space drastically. I think additional benefits are like, you don't really need specialized data set. You don't need to download mocap data to get the pre-grasp. You also don't need people to just carefully learn about teleoperation, learn about performing the task to do a full demonstration collection. I think anyone could do it. Also, it's a really short amount of time. You can just play around in the simulator, put your hand around the object for like 1 minute or so, and then you get these nice initialization data.
Yeah, so I guess in layman's term, if I can just restate what you said, so it's kind of like you get the humans to do something in simulation where you just roughly learn where would humans even put their hands, but just roughly speaking. And then that already limit a lot of the, like, shrink your whole search space or exploration space so that you don't have to run so many simulation run. And then from there on, the detailed stuff can just let the simulation do its thing.
Yeah, exactly. So I think the lesson that I got is that a little bit of human prior, just a little bit of it, can really speed up policy learning by a lot, can really help with exploration. And you don't really go over the board and do fancy things. And this kind of simple initialization is really what can help a lot.
How long does it take to train the policy like this? How many GPUs do I need?
So for the grasping policy, it's actually relatively short, as I think I train on 8, or actually I train on 4 L40s. And then for less than 24 hours for each of these grasping policies. For lifting, it's similar. And then for Handover, I think I train it for a little bit more, 2 to 3 days. But I think what's interesting about the Handover policy is that because I think the state that gets you to the successful trajectory is relatively sparse, it's still a sparse reward task. So it's really like either you get it, and once the policy get it, it learns really fast. So you see a step curve kind of training curve where there's a long period of 0 reward and suddenly it shoots up. And after that, it's just all success. And because of RL, there's really no way to predict when it will get to the point where it reaches that moment of joy. So sometimes it's 1 day, sometimes less than 24 hours. Sometimes it's 2 days.
This again comes down to exploration, basically, because like the handover is like a longer horizon task, and it's just harder to get the exploration right. It's like these the initial guesses and all don't help quite as much, I guess. Is that right?
Exactly. Yeah, it's all like the same problem you get with RL.
Yeah, makes sense. So, okay, earlier you mentioned these are out of distribution objects. How many grasp policies did you train? And like, what are they, and what does each one do, I guess? Small objects versus larger, is that kind of,
So they're actually all the same policy.
Okay,
so
right.
just a single grasp policy. I think, for example, all these 4 videos shown here comes from the same grasp policy. I think an interesting thing, maybe it's something with RL sim true, is that sometimes there are a lot of bad policies that can't really be sim true, can't really do grasping. But once you get a successful policy, once you get a really nice policy, it's capable of doing everything. Yeah, like winner takes it all, I guess. I think once it learns the right distribution of object, the right behavior patterns, then I just keep using that policy. Yeah, it does amazing work like this, grasping out of distribution objects, grasping very small objects. I think I really like the finger movement of this, where it adapts to the sizes of different objects. And also the emergence of different grasp patterns depending on the object state, which means it's actually really adapting to different object states that it perceives. And also, of course, robustness and recovery, they also really like from
Can we
different
ask a
tasks.
really unrelated question? So I'm assuming this is like the Gear Lab kitchen. There's like a tether tied to the drawer back there. Were you trying to open that with this policy too or something? Is that a...
Yeah, actually, no,
Yeah.
that's very good question. That's a your kitchen indeed,
Yeah.
but no, I wasn't really trying to do that.
Okay. All right.
You could
Go
also,
on.
yeah, I didn't even notice before you mentioned it.
Like there's like the blue tape and everything too. You can tell someone was running some experiment before you took this.
Yeah. Yeah, actually, now I've noticed. Yeah, maybe it's the education learning policy where you need a marker. I don't know.
Yeah.
Yeah,
It happens.
Yeah.
Okay, Toru, I have a question. I come across so you have this chart in the paper where you kind of show the success rate for a couple of these tasks, and then I think the x-axis is like number of environmental like variations or something like that. And I see that they kind of plateau at around 50-60% success rate. Do you want to comment about that? Like, what do you think we could do in future work that can really get it plateau a lot higher?
Yeah, that's a good question. And that's also related to, I think, the limitations of this work, which are things that I did not address. So I think, first of all, of course, the hardware limitation, we couldn't really get a more dexterous hand, which ideally we want the finger movement to be more agile. We want the degrees of freedom to be more so that it's capable of really grasping more objects and handling more different shapes. So that's one. And the other thing is that in this work, I really didn't do anything other than domain randomization to close the center gap. Yeah, so I think all I did was to randomize on things like object position, the observations, the robot masses, robot damping, stiffness, and all that parameters. I think there are more recent works that try to more explicitly address that by doing things like doing, for example, online explicit sys-ID. That maybe there's a more accurate physics model that the policy can be used to do the policy rollout better. Yeah, or other things like randomize with a smarter domain randomization noise when you do the policy training by doing some tests first to identify the actual gap between the sim and the real so that you don't really over-randomize, which means that sometimes for some of the parameters in sim, maybe you end up adding too much noise. And the result of that is that even though the policy could be some true transfer, because your data distribution covers the real physics, but because of the noise you added is a little bit too much, the policy you learn isn't really optimal. You can imagine that if you are in a very noisy environment, the best you can do is to learn an average policy that can address to all the environments quickly, but it doesn't really excel in a lot of these environments.
Yeah, I was wondering also like this real to sim setup with the auto tune model. Going to the minimums like MSE, right? Basically. So, do you think there's still more things you can do over there, or like at least for that part of the stack? That's so because it sounds like what you just said. It's maybe the improvement is towards more sim to real, like later stage. But I was wondering whether there's still more things you can push if you can get the real to really match the real to sim and the real and the sim to be as closely as possible, basically matching your URDF with the physical parameters.
Yeah, I think definitely. There's actually a work from, I think, Rust Tedrick's group recently that I really like. I forgot its name, but I think it's a paper showing how you can use a gripper. You take an object, you kind of like randomly shake it or perform some kind of handling of the object, and then in the process, you identify the actual physics parameters so that you can match the sim dynamics and real dynamics. So I think it really addresses the real to sim modeling problem that here my work doesn't address, which is how do you close the modeling gap in dynamics? But then after a closer look at that work, I also realized that it's not super straightforward to me how, if I were to do it again, how I could have done it. Because I think to do that, you also need to rely on a physics parameter that really has much more accurate object physics, which I don't think Isaac Jim is there yet, but I will keep looking. Yeah, but I think, yeah, very good question. I think on a high level thing, what I really miss in this work, what I hope to address in the future is really the gap in dynamics, either in the real to sim modeling part or the sim to real transfer.
Can I say, so one thing that kind of bothers me, and is that it's the the third person camera thing, because I really like mobile manipulation, and like I feel like it's hard to have like a second view of everything unless you've got like two robots moving together. So do you see a way that you could get rid of that constraint on this, or like what happens if you don't have that third person camera? Does stuff just not how well do things work?
Well, I guess in that case, maybe switching to a camera with larger field of view is the solution, because I usually take my inspiration of how humans are designed. And when I think about ourselves, yeah, we have a pretty large field of view because we have had. And another thing is activation. So we actually have another work on activation coming, not released yet, but stay tuned. I think that's another way to address this, because then you can just intelligently move your head. You can look around, you can search for objects and do other things.
Yeah, that makes a lot of sense.
Yeah, so I guess maybe it's to wrap this up, like well, it sounds like you already briefly mentioned some of the future work using active vision. Is there any other thing that you think if you were given maybe 1 or 2 more months, what would you have squeezed into this paper?
Oh wow, that's hard. Yeah, I think definitely better, as I mentioned, the dynamics modeling part. I'm not sure whether I will squeeze into this paper though, because I think it's already quite a mouthful on the title. Not sure whether it's a good choice to add more. But definitely if I were given time to do a next project, unlimited budget and frozen time and all that, I think the most important problems to address are, closing the dynamics gap in both the real to sim modeling part and the sim to real transfer part. And then I think there's also something that I think could be important is the object perception. I think again it relates to both the real to sim modeling and the sim to real transfer. So I think, for example, one thing that I see a lot of recent works already doing is how to scan an object with a camera and then translate it to a 3D object. So things like that, I think would also really help with sim to real transfer and policy learning.
Yeah, Chris, do you have more questions? Otherwise, we can ask the usual last question. Very last question is there any cool papers that you come across like recently you want to give a shout out to that you completely blew your mind?
Yeah, I will say I like the real to sim modeling paper. Let me see if I can remember the name of that. A scalable real to sim, actually. That's the name. That's a really interesting name. So I will share it here. I like this work as from Russ and Philip, I think two professors that I like and respect. And as I mentioned, they're able to get a robot gripper to just grasp or play with an object. And then, by playing with the object, it can identify the physics pretty accurately. And you can see my website is loading, but you can see pretty nice results from their identified physics. You can see there's a pretty small gap between the real and sim. So this is what I like.
Cool. Yeah, we'll definitely read that paper. Okay, cool. Thank you so much, Toru. Thank you so much for your time.
Yeah, thank you.
Bill.
A lot of fun. Great. Really cool work. Yeah, looking forward to seeing the next stuff.
I'll keep working. And thank you so much for the nice comments and summaries. Yeah, thank you. It was a joy chatting with both of you.
Yeah, thanks.
Likewise.
It was great.
Thanks for making time. Yeah, so what do you think, Chris? What have you learned? Any thoughts?
Yeah, I thought it was a lot of fun to hear about the journey that led to this. Toru started with imitation learning on like for dexterous hands manipulating objects, and then she went from there to RL with like in sort of a simple case, which is just state-based proprioceptive RL with like these very dexterous hands, and now is getting closer to humanoids, and it's really tracked, honestly, the way that I feel like robot hardware has been progressing, where we've gone from like these old industrial robot arms with like really kind of crummy hands on the end. Well, maybe they were okay. But then like all the way up to like this fancy looking Fourier humanoid that she's been experimenting with, right? So It's definitely like, it's a nice snapshot of the way the field's changed over the last few years, to be honest, it feels like. But yeah, aside from that, I mean, I really liked seeing all the results look really nice, seem to real. It's a very compelling story about how to get these dexterous real world policies going. A lot of interesting tips and tricks about what works for reward engineering, which is kind of the bane of anyone who tries to do like lots of RL, is like, how do you get this stuff to really work? Because exploration is really tricky. There's lots of stuff. I don't want to talk too much.
Yeah. Yeah. Well,
what do you think?
What I find really intriguing is that, like, even though supposedly the whole thing is nearly everything is simulation, but actually there's still a small part that actually involves the human, right? What you call task-aware hand pose.
Yeah.
And by having human in the loop just for that part, drastically reduce the the search space or exploration space, so that now it becomes a tractable problem. So I think that alone is interesting to point out. I thought that actually that humans in the loop actually move the needle a lot is the only thing, is one of the main key thing that, in my mind, that allow her to, with the compute that she has, to still make something, work. So that's still a part I think humans can play. The other thing I find quite really cool was that whole auto-tune model, like, just automatically kind of map the correct, let's say, URDF, robotic parameters to the physical parameters. So I can imagine it's so hard to hand code that it must be damn frustrating to do that. Yeah. So I thought that was really cool. Anyway, cool. Well, let's do this again next week.
So it's tough. Yeah. Talk to you later.